We'll look at lime soda ash softening as a process. Objectives of lime soda ash softening, and it's really true for all softening processes. So we want to reduce the concentration of calcium and magnesium. We want to produce water that's at an acceptable pH. And if necessary, we want to reduce the concentration of other metals to meet drinking water standards. So for example, in the thumb area, arsenic levels in the groundwater are often quite high. So if they're using lime soda ash softening, they can also achieve arsenic removal in some cases and be able to meet the drinking water standards for arsenic using lime soda ash softening. Now, lime soda ash softening is limited by the solubility of these minerals. So at 20 degrees C, calcium bicarbonate has a solubility of about 170 grams per liter. On the other hand, calcium bicarbonate has a solubility of about 6 milligrams per liter. Okay, so this is 170 grams per liter. This is 6.2 milligrams per liter. So you can see this is actually plotted on a log scale here. And if we start at a pH of 7 here, and we increase the pH, let's say to 11, we have a decrease from about 5 times 10 to the minus 3, and this is in moles per liter, down to about 9 times 10 to the minus 4. So about an order of magnitude decrease in the concentration from a pH of 8 to 11. The reason this is the case is, if you look at this plot here, if we're at a pH of 8, then bicarbonate predominates. If we raise the pH to 11, then the concentration of bicarbonate decreases and the concentration of carbonate, so you can see at pH 8, the concentration of bicarbonate is on the order of 10 to the minus 6. Sorry, the concentration of carbonate is on the order of 10 to the minus 6. But if we raise the pH to 11, then we have a concentration of around 10 to the minus 3. On the other hand here, if we start at pH 8, we're at about 10 to the minus 3, the log of the concentration, and we lower it to about 10 to the minus 4. So we get about 1 log or 1 order of magnitude decrease. So what we want to do is we want to produce calcium carbonate because the solubility is much less than that of bicarbonate. So in order to do that, we want to raise the pH. Magnesium bicarbonate, so if we start at a pH somewhere around neutral pH, where bicarbonate predominates, the solubility of magnesium is 37 grams per liter. However, if we raise the pH to where carbonate predominates, we can reduce the solubility by about 3 orders of magnitude. However, if we can precipitate that magnesium as magnesium hydroxide instead of magnesium carbonate, the solubility decreases by about another 2 orders of magnitude. So starting at a pH of, let's say, around 6 to 7, where bicarbonate predominates, we have a solubility of magnesium bicarbonate of about 37 grams per liter. But if we can raise the pH to where we form magnesium hydroxide precipitate, the solubility drops to about 10 to the minus 2 grams per liter. So we're in the milligram per liter range. It's about 10 milligrams per liter. So this is actually about 10 milligrams per liter. And you'll see this, we'll talk about this in just a little bit in terms of process limitations. So we can also achieve removal, as I mentioned, of other species. So we can remove iron and manganese. And it's interesting with MSU. MSU has softening, as I mentioned, as point of entry systems in a number of the residence halls. When they were debating whether to build a new water treatment plant, they could have softened the water at the plant, and that would have eliminated all of these point of entry systems. Or they could have just achieved iron and manganese removal. For whatever reasons, and most likely cost, it was chosen that they would simply do iron and manganese and not to soften the water, which means that the res halls still will soften water. It will also remove naturally occurring organic matter, essentially a precipitation reaction, that the organic matter gets incorporated into the precipitate and settles out with the precipitate. And the same is true with turbidity. It also can potentially remove other metals. So for instance, if we look at zinc and we start out at a pH of 7, so we start here, and we raise the pH to about 10, we decrease the solubility from about 100 milligrams per liter down to 0.1. But notice, as we raise the pH, we actually increase the solubility. If we go up to 11, we're at a solubility of 1. So we can get about a 99% removal, actually, ideally, in this situation. So it doesn't, solubility does increase, but you do get some removal. Nickel is here. You can see nickel. You get very good removal if there was nickel in the source water. Same with cadmium. Not true for lead. Lead is a challenge. Copper, you would get removal. Chromium, notice the solubility of chromium has a minimum about 7.5 and then actually increases significantly beyond that. So chromium, we could not remove with lime soda, not to any appreciable extent could we remove it with lime softening. So these are the reactions that occur. As I mentioned, it's a significant amount of chemistry, but if you simply think about it as balancing an algebraic reaction, hopefully it becomes a little more straightforward and less challenging. So as I mentioned, groundwaters will often contain CO2. So the first reaction that we need to do is to neutralize that CO2. We get no, notice here, we get no hardness removal. We're simply increasing the pH. So the goal with this first reaction here is to neutralize the CO2. So we add lime. This is actually shown as hydrated lime. Hydrated lime, what we typically add is quicklime, and that we hydrate at the plant, and that produces calcium hydroxide, or hydrated lime. So we precipitate the CO2 and hydrated lime as calcium carbonate. So we're producing a sludge. So I've shown the sludge that we produce, the solid residual, in green. I've shown the chemicals we're adding in blue and the reactant in red. So we're removing calcium. The second reaction is a precipitation of carbonate hardness due to calcium. So it's that calcium associated with bicarbonate. We add lime, and notice here, we're actually adding calcium to remove calcium. And it's a 1-to-1 stoichiometry. So for every 1 mole of calcium we remove, we need 1 mole of lime. But we produce 2 moles of sludge. So we produce a significant amount of sludge from this reaction. Second reaction is the precipitation of carbonate hardness due to magnesium. So this is the magnesium that's associated with bicarbonate. For every 1 mole of magnesium, we need 2 moles of lime, and we will produce magnesium hydroxide and calcium carbonate. So we produce 1 mole of magnesium hydroxide, 2 moles of calcium carbonate. In order to achieve this reaction, we need to increase the pH to 11.3. So we need a high pH. Here we're typically operating at about 10.5. So we need to increase that pH significantly above what we need to remove the carbonate hardness due to calcium. Then we have the reactions for the non-carbonate hardness. Here we have to add soda ash. Sodium carbonate is referred to as soda ash. So for every 1 mole of calcium we remove, we need 1 mole of soda ash. We will produce 1 mole of lime. And notice we're also adding sodium ions. To remove the non-carbonate hardness due to magnesium, we need lime, we need soda ash, we will produce magnesium hydroxide, we also produce calcium carbonate sludge, and we add more sodium. Basically, it's more expensive to remove non-carbonate hardness than it is to remove carbonate hardness. So if we can avoid removing the non-carbonate hardness, we will. If we can avoid removing the magnesium but still produce desirable quality water, we will avoid removing magnesium. Now there are process limitations. As I mentioned, the solubility. I showed you the solubility of calcium and magnesium. So some hardness ions will remain in solution. That is not true when we talk about ion exchange or reverse osmosis, or to a much lesser extent. But with lime soda ash softening, your solubility, because of these limitations, you will typically produce a water that has about 40 milligrams per liter as calcium carbonate. And that's because, one, solubility. The other thing is that solubility reactions are not rapid. It's unlike an acid-base reaction, which is almost instantaneous. Solubility reactions are time dependent, and there may be incomplete time for a complete reaction to occur within the flocculation basin. There's also non-ideal mixing. We've talked about that. We've talked about short-circuiting. I mentioned that, and that can result in process limitations.